Good morning, ladies and gentlemen. May I have your attention, please? Wonderful, thank you. At this time, I ask that you raise your hand if you do not get a red mark for today, the 30th of September. Very good. Okay, let's go ahead and get started with our discussion. So I noticed that I was coming around that some people were missing a very important component of our definition of a limit. I'm sorry, our definition of the derivative. It involves a limit, right? That's what's going to allow us to get past that average rate of change notion of a function over an interval to the instantaneous rate of change at a particular x value instead of over an interval. When we let that interval shrink to 0, right, we get away from the average rate of change and the slope of the secant line, and we end up with the instantaneous rate of change and the slope of the tangent line. And that's the key point. And so if we're missing that, we're still just dealing with an average rate of change over an interval. We need the instantaneous rate of change at a particular x value. So our definition for the derivative of a function f, right, at x equals c, is given by f prime of c. And we write that little apostrophe there to denote the first derivative. So that's f prime of c. That refers to the first derivative of f evaluated at x equals c. And that's given by a limit expression. It's the limit as x approaches c of f of x minus f of c all over x minus c. We had that as our closure from last class, right? We moved beyond average rate of change over an interval to instantaneous rate of change at a point. What gets us past the average rate of change? Well, here, right, we have some interval from x equals c, right, to some arbitrary x. And if we let that x value get close, the arbitrary x get closer and closer to the particular x value, right? If we let that interval shrink to 0, now we're dealing at a single x value at x equals c. So we need this limit in order to get instantaneous rate of change. That is the first derivative. Awesome. Let's use it to do something. Right? Let's go ahead and get the derivative then, the derivative value of my function f at a particular x value. In this case, at x equals 1. So we'll go ahead and start with our definition of the derivative, except this time we have our c value. Everywhere we see a c, we're going to use the particular x value of concern, x equals 1. So instead of having f prime of c, we have f prime of 1. And that will be given by the limit as x approaches 1 of f of x still, so we still have f of x, minus f of 1 all over x minus 1. Because we have a particular function f of x delineated, we know what f of x is. We can replace that with my algebraic expression, x squared minus 4x minus 1. Because we have a particular function f delineated, we can get the value of my function f at x equals 1. So both of those numerator terms can be replaced. Let's go ahead and rewrite this as the limit as x approaches 1 of, what's f of x? X squared minus 4x minus 1. Minus, and now I'll do f of 1. What's f of 1? Well, let's go and see. I'll plug in 1 into my expression f and see what the y values return. So 1 squared is 1. Minus 4 times 1 would be negative 3. Minus 1 is negative 4. So f of 1 is negative 4. All over my arbitrary x, right, minus my c value. My c value is 1. So there we've got our f of x minus f of c all over x minus c. We put in our particular value, right? Our particular c value is x equals 1. We evaluate my function to get f of 1, and now we're ready to do this algebraically. We don't need any decimals. We don't need any small step 0.001. We don't need any delta table. We don't need any t step, right? We're good to go with this. All right. So if I were to try to evaluate through direct substitution, I know I'll get a 0 on the bottom of a fraction, right? And that's undefined. So I'm hopeful that with some algebra, we'll be able to rewrite this in such a manner that my x value concern, namely c equals 1, is in the domain of my expression. So let's go ahead and try. Let's consider the limit as x approaches 1 of x squared minus 4x minus 1 plus a negative 4. I'm getting x squared minus 4x minus 1 plus 4 is going to be plus 3. Is that what you guys are getting? So x squared minus 4x plus 3, is that the numerator? All over x minus 1. Direct substitution yields 1 minus 4 is negative 3 plus 3 is 0 over 0. But it's an indeterminate form, and that's great news. So what might be some tools to rewrite this? Colin?
Factor.
Let's factor, right? I'm down. Let's factor. So we'll rewrite, keep your limit expression just like we did last unit. We'll go ahead and factor that numerator, be ready to share. So what will our numerator factor into then, James?
X minus 1, X minus 3.
So x minus 1, x minus 3. Because we're evaluating a limit and x doesn't equal 1, we can play my favorite game. Yes, that's right. The cancel game. And we'll now get the limit as x approaches 1 of x minus 3 is my x value of concern in the domain of my expression. It most certainly is. So I can evaluate through direct substitution and get 1 minus 3 is negative 2. Raise your hand if you had negative 2 via any method. Negative 2 via any method, so we can interpret what that means. Raise your hand if you did it algebraically without a calculator using our limit definition. Good. So we need to be able to evaluate limits. That's why one of the reasons, right, that we spent kind of that whole unit 2 dealing with limits, and they had our algebraic evaluations, right, so that we're able to manipulate expressions. If this is on non-calculator portion, right, non-calculator portion, we still need to remember how to evaluate limits. Now don't worry, we will generate shortcut rules for finding derivatives, right? We will generate that. But the basis for those rules comes from the limits, the definition of the derivative, and our limit theorems allows us to evaluate it. So we can't lose sight of that. We'll be able to use those shortcuts once we verify them, and that'll be great and a time saver, but we can't lose this foundational stuff. Awesome. So big whoop. What does that negative 2 have to do with anything? Well, what does that derivative value negative 2 represent? What did that tell us about anything in the original problem? Vivian?
It tells you the instantaneous rate of change.
Absolutely. That gives me the instantaneous rate of change at x equals 1 in this case. And so if I went to that function, f of x, it should be changing at a rate of going down 2 y units for every 1 x unit that I scooch over from left to right as I move along it. Math man or math woman scooting along the function. So at x equals 1, the slope of the curve is negative 2. At x equals 1, the slope of the line tangent to the curve, right, is negative 2 as well. And that's the same thing. So the instantaneous rate of change, all that, at x equals 1. That's also the slope of the curve or slope of the tangent line. I'm going to say and. I'm not going to say or. It's the slope of the tangent line and the curve at x equals 1. If you zoomed in at that point of tangency repeatedly, right, and that curve would stretch out and resemble, well, exactly the tangent line, right? Exactly the tangent line. They would both appear linear, and that's what we'll call a concept of locally linear. For functions that are differentiable, right, at x values, they're called locally linear. If we were to zoom in on that curve more and more and more, it would look exactly like the tangent line. Let's now go ahead and find the equation of that tangent line. Choose one of the biotech fields here. Should I give it back to you? Yeah. Okay, thank you. So recall from last time that you could use y equals mx plus b, or the College Board recommends using the y minus y sub 1 equals m times quantity x minus x sub 1. Now you could do it either way. It's just that the y minus y sub 1 point slope definition more easily translates into linearization, a topic, an application of derivatives later. So it might be useful to start out with our y minus y sub 1 equals m times quantity x minus x sub 1, where m is our slope.
Pardon for a second, can I get back to
Yeah. And my particular point of concern, that is the point of tangency, was given by my x sub 1 comma y sub 1. All right, so let's go ahead and do it. Go ahead and be ready to share with the class as I go and generate my equation. What am I going to put in where? So what's my y coordinate of the point of tangency? Danny? Negative 4 is my y coordinate of the point of tangency. We evaluated that with f of 1, negative 4. Good, thank you. What am I going to use for my slope of the tangent? What are you going to use for the slope of the tangent? Gabby? Negative 2, that's my value of the derivative at x equals 1 that we calculated. What am I going to use for my x coordinate of the point of tangency? Like 1, thank you. And so there's our equation we're going to generate. We start out with point slope form. Now this won't do any good for us in terms of entering in our grapher, so we want to make sure we solve. So after solving, can I do a dot, dot, dot? We get a y equals, I'm going to get negative 2x plus 2, right? And then minus 4, so I'm getting negative 2x minus 2. For the equation of the tangent line. Raise your hand if you already generated that. So did anybody else get negative 2x minus 2? That's good news. Let's go ahead and verify that graphically. I'm going to go ahead and put that in my calculator now. And we'll graph that tangent line on the same viewing window. As the actual curve. And so I've gone ahead and with my emulator, I've entered the function. I want to add to that our tangent line. So negative 2x minus 2. Obviously we want that. And let's go ahead and graph. Ready? Here we go. There's our original in blue. Here comes the tangent line in red. I'm hopeful. If I were to jump on the curve, my original function, at the x value, x equals 1, trace 1, enter, voila! The cursor will appear on the point of tangency. And does it appear that the tangent line touches the curve at this point, 1, negative 4? Yes, it most certainly does. And my equation of the tangent line then is verified, right, visually. So visually we've done that. Okay. So let's go ahead. Are you guys good with that? Verify that that's tangent line? Okay, so now this is where, right, we open Pandora's box and we say, here's some more graphing calculator technology, but I don't want you to rely on this and do it all the time. I want you to use it as a means for checking what you can do algebraically. So ready? Here we go. We're going to clear out our tangent line. Get it out of there. Now we're just back to our plain Jane function in blue. There's our parabola. Ready? Now we're going to draw a tangent line with our calculator. So we're going to do second program is the draw menu. And we're going to go ahead and draw a tangent line. We're going to draw a tangent to the curve. And where are we going to draw that tangent line? We're going to draw it at x equals 1. So I'll tell the calculator the x value concerned. I want the calculator to draw a tangent to my curve at the x value, x equals 1. So I'll do second program is draw, tangent, enter, and then I'll enter the x value concerned. That's 1, enter. And voila! The calculator draws a tangent to the curve, and that's not all. It spits out the equation of the tangent line right there. So it tells us the equation of the tangent line. Now, that would be way quicker to do it that way. If for calculator allowed, you certainly may do it that way. Please note that you oftentimes will get negative 1.9999863. And you have to recognize the calculator is doing its darndest to tell me negative 2, right? Plus a negative, 2.0000468. Well, it's not really 2.00468. It's really 2, but the calculator uses approximation, including a symmetric difference quotient, to get the estimate of the derivative and so on and so forth. So your calculator is only going to give you a decimal approximation. It worked out very nicely and actually gave us exact, maybe because I changed my window around when I made this picture. The first time it gave me decimals. And so here we go. That's pretty great. So we can do second program is draw, tangent, x value of concern, enter. And it'll do it for us. We want to do that right now for verification. We still need to do it algebraically because we have to be equipped. We have to be able to handle this on a non-calculator portion of the exam and a calculator lab. What questions do you have about our bell work then? Okay, along involved bell work, but I was a little concerned with our definition of the derivative as I walked around, right, and being able to calculate this algebraically. You have to be able to do that. Let's go ahead and extend this now at a different x value. So we're not going to do the equation of the tangent line every time. What I do want to do, however, is do another algebraic evaluation. So let's go ahead and now find the value of the derivative of my function f at x equals 2. So let's go ahead and take a look at this. We'll start with our definition. I know that f prime of c is given by the limit as x approaches c of f of x minus f of c all over x minus c. In this case, I want f prime of 2. The value of the first derivative at x equals 2. So what will we do? We'll go to our original. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2. And we know these things. We know what f of x is. So f prime of 2 must be given by the limit as x approaches 2 of, what's f of x? Well, that's x squared minus 4x minus 1 minus, what's f of 2? Well, we need to go and figure out what f of 2 is. So we'll go to our original. F of 2 is 2 squared is 4, minus 8 is negative 4, minus 1 is negative 5. So f of 2 is negative 5 all over x minus 2. There's my x value of concern. Okay, go ahead and finish this out with your partner algebraically. We're no 1.001, 2.001 on our calculator, right? No symmetric difference quotients. No y sub 3 that you saved in from pre-calc last year. And your y equals many and just turn it off by highlighting the equal sign and pressing enter. I know who you are. Instead, let's go ahead and evaluate this algebraically. Be ready to share. So what did you get for the value of f prime of 2? So what did you get for the value of f prime of 2? Maggie?
0.
0. Raise your hand if you got 0. Roll 0. 0. Great work. Awesome. We could go ahead and do the same thing at a different x value. I don't think we can do that each time. We could go ahead and do the same thing. I'm going to jump right to my definition. F prime of 3 will be given by f of x is now x squared minus 4x. If you get better at this, minus f of 3, right? F of 3 is going to be given by 3 squared is 9, minus 12 is negative 3, minus 1 is negative 4, all over x minus 3. So we can go ahead, don't forget the most important part of the definition of my derivative. This is the limit as x approaches 3. We have to have that limit, right? Otherwise, we're not doing an instantaneous rate of change. We're doing an average rate of change where my interval is 0 and I won't be able to get around that 0 in the denominator. All right, dot, dot, dot. Okay, go ahead and share with the class then when I call on you. What did you get for the value of f prime of 3? F prime of 3. Tyler? 2, raise your hand if you have the same as Tyler. 2, 2, absolutely, good job you guys. So, in each case, what does this represent? Well, we can use Vivian's interpretation from before. This is the instantaneous rate of change of my function f at x equals 3. Or the slope of the curve at x equals 3. Or the slope of the tangent line to the curve, right, at the point when x equals 3. All of those are equivalent. So we've got some first derivative values, right? We've got some first derivative values. We've got some function values. What I want to do is ask, how do our results compare? Well, they're all numbers. Okay, we've got all numbers. Some of them are positive, some of them are negative. What do those results represent graphically? We've seen that as the slope of the curve or the slope of the tangent line to the curve. I want to focus in on 3. Was the derivative value of f of x the same regardless of the point of interest? So was the derivative value the same regardless of where we were looking, Grace? No, it's different. That change itself, depending upon where we're looking, right, the derivative will produce a different value. Well, the derivative then is a function itself. Depending upon where we're looking, what x value concern, what input value we plug into the derivative, it's going to output a different value. We've got several of them. Let's go ahead and record our findings. So if we were to plot, and this is algebraically, if we were to plot some points on our original function, we've already done f of 1, and we had f of 1 was negative 4. So 1, negative 4, let's carefully plot that. F of 2 was negative 5, so let's go ahead and plot that carefully on my original function now. 2, negative 5. F of 3 was negative 4, we did that in our third derivative evaluation when we found f of 3. So we'll plot that. If we continue choosing some more x values, we would get 0, negative 1, I've got that one. And 4, negative 1, we can plot that. Now let's carefully connect that in a nice smooth parent function parabola. We already saw that from our graphing calculator and Bellrock, but I want to do it algebraically here. Now let's go ahead and add our x comma f prime of x as points on a derivative function f prime. So what values do we know so far? Well, we know one value. At x equals 1, what was the value of f prime? Joel? Negative 2, thank you. At x equals 2, right? At x equals 2, that was our second algebraic calculation. What was our value of the derivative? Namely, what's f prime of 2? Kyle? 0, thank you. At x equals 3, what was our value of the first derivative? Andrew? 2. If we go ahead and plot these on the same xy coordinate plane, right? We've got 1 comma negative 2 would be right here. We've got 2 comma 0 would be right here. We've got 3 comma 2 would be right here. And there's nothing special about these x values of concern 1, 2, or 3. We could do the same thing with our definition of the first derivative and an x value of concern of 0 or 4. And we see that the same trend continues in both directions. And so if we completed this pattern and now connect these in a nice curve, this would be like a curve without a curve, right? What type of function was my original? My original function in green, what type of function was that? Katie? A quadratic function. What type of function was its derivative shown in blue? What type of function was that? Gabby? Linear. And so we've got this quadratic function original, we've got this linear. And I know that you did an activity investigating polynomials in pre-calculus and an FST/pre-calc compacted. And so there's some things that we can assume when dealing with polynomials, right, that you developed last year that will hold true now. If we have a second degree polynomial for our original, then guess what? Our derivative function is going to be first degree, right? We're going to step one down degree from that, and that's great. What conclusions can we draw by looking at the graphs? I want to hold on that. So we'll go ahead and add that later. For now, we'll be able to rely on this as we generate our discussion for our sketching derivatives as a function. Okay, great work so far. Let's go ahead and take care of our OTL number 3. At this time, please make sure that your name, 1B, and number 3 are clearly labeled on top. If you need a stapler, we'll go ahead and send that around if you need a stapler. Anybody need a stapler, you can use one on the side table or there's one up here. Give yourself credit for those who complete out of 13, please. Divide, enter, multiply by 2, and let's box your infinite canvas score nice and big on top, down to the nearest 5.0 to 2. After making sure that your name, 1B, and number 3 are on top of your assignment, your infinite canvas score is boxed. Go ahead and pass from back to front, please. Front rowers, make sure they're facing the same direction. I appreciate your help, and I'll come and collect them. Just make sure you put that in the front of your credit. That's it. Yes, sir. I'll get it out of your face. Thank you. Ready to go with number 3 if you did it? Number 3? Okay. So in just a minute, we're going to go ahead and be using the stat plot and the list editor feature in my graphing calculator, right, to inspect a different function and its derivative. And we're going to do that via the softball pop-up problem. So because I have the microphone plugged in, the USB, it's not running the sound through there. It wants to push it out through a little headphone jack in the preamp there, and so we don't get to hear the balloons, but I think they might be there in the recording, so I'm just holding out for that. Obviously, I'll be reviewing that after class because I feel like that was an empty balloon, like a dry balloon. You know, we don't want that. We want the water balloon. You know, we want to hear it. Okay, so what we're going to do is we're going to do a little jigsaw now. If everyone would find your softball pop-up problem. It's the one where the softball player hits a pop-up and it's got the screenshot from the TI Inspired Graphing Calculator. Derivative out of point C. We just did that and bell works several different times over. Consider the situation. A softball player hits a pop-up. An equation to describe the height of the ball for a given time is given by h of x equals 1 plus 25x minus 4.9x squared, where x is the time, t in seconds, and h of x is the height of the softball above ground in meters, all right? We're going to go ahead and break up, and we're going to divide this into 1, 2, 3, 4, 5, so 6 groups. And what we're going to do is we're going to go just number off around the room, starting with at x equals 0 is going to be your assigned point. X equals 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, up. Did I go to 6 twice? I went to 6 groups? Yeah, okay. So the 6s are now changing to 0 and a 5. So whoever was 6, you were 6. So you're going to be 0 and you're going to be 5. Yes? Okay, now you're going to go ahead and go through. You're going to start out with the definition of the derivative in number 1 and write an instantaneous rate of change. You're going to go ahead and ultimately use the end derivative option or tables, right? So you can use your tech tip method 1 or tables to analyze, and then make sure that you get a decimal value with the correct units. When you're done, raise your hand. I'll come over, and then I'm going to have you guys come up and write on the smartboard, right, your result. Awesome. So work with your partner to do that, unless your partner must. Raise your hand when you've produced a value, and then I'm going to come around and check you out and send you to the board. I'll pause the recording and then we'll resume when we have our table filled in. So here we've got our class data, and we're going to enter that in our graphing calculators. We've got our original function entered in our y equals menu. We've gone ahead and included our modified window to match the screenshot for the Inspire on our pop-up problem. We'll do a quick check and make sure we produce the picture on our handout. And now we'll go ahead and add our class data. And so we're going to add our class data that we just generated from last time. So here we go. We're going to go, where do we do that for class data? We go to stat menu. So everybody, we're going to do stat, edit, and in list 1, we're going to put our time values. So if you have data already in your list, you can up arrow to highlight the list title and press clear to delete it. And then down arrow, and you'll clear your list out. Alternately, you can do clear list as a command, clear all lists. But I'm going to go ahead and just up arrow to highlight the list title and clear out. I'm going to enter my x values 0, 1, 2, 3, 4, 5. I'm going to enter the corresponding h prime values. My h prime of x values are respectively 25, 15.2, 5.4. Everybody do it, negative 4.4, negative 14.2, and negative 24. Take a minute to make sure you have the same number, right, of values in each of my lists. Otherwise, we'll not be able to do the pairing and we'll get an error when we try to do our stat plot for dimension mismatch, and we don't want that. So we've got our stat edit. We've got our class data in our list of 1, comma list of 2. And let's go ahead and do our stat plots. So we can go ahead and go to second y equals, and we want to pair list 1 with my independent with list 2 my dependent. So list 1. So I'm going to go ahead and do that first one, plot 1. I'm going to turn it on. Alternately, you can just toggle above. Blue. Then I have the other one in blue. Yeah. That's my horn, though. Turn it on. Let's go ahead and see what happens there. Awesome. So that's fun. So we've got our window. We've got our stat plot. And we've got our plot 1 graph. Awesome. So what do we need to do now? Let's do a regression and get the equation that best fits those data points. And so where do we go to get a regression? Stat calc, comma baby. So let's go stat calc. I want the 4th option there. The 4th option, because it looks like a line. And I wanted to find the regression that pairs independent list 1 x values with dependent h prime of x list 2 values. I'm going to store the regression equation because I like it in there in a graph already. So Alex, we can use the same vars, y vars function, and I can store that in, we already have a y1, so I'm going to store it in y2 so I don't overwrite my original. And that'll automatically put my regression equation in my y equals menu so I don't have to write it down and then retype it in for the birds. Well, let's go ahead and calculate. So there's my calculation. It looks like y equals negative 9.8x plus 25, but I'm dying to see the graph. And so here's my original in blue, my stat plots in red, and here comes y2. Woo-wee! So how our regression line, how does it fit the data? Spot on, right? Spot on. So that's good news. And what conclusions then can we draw? So as I look at this picture, okay, what relationship exists between an original function and its derivative function? Before I close that out, I want to grab this. All right. So what relationships exist between an original function and a derivative function? What I want you to do is go ahead and talk quietly with your partner and be ready to share. Be ready to share two things, right? Be ready to share two things. Two relationships or connections between an original function and its derivative.
Degree lower. Because
Oh yeah, the slope lowers out here.
and then that's the vertex, right? Yeah, the vertex. So it's
Okay, what's one connection between our original function y and its first derivative function y prime? What's one connection? Blake and Riley?
the derivative is 1 degree less than the original function.
So our original function, right, if our original function was degree 2, as is the case with this quadratic, right, then our degree of the derivative function was 1 less. Is that right? Okay, so, and that's true so long as we're dealing with a polynomial function. So, right, so for polynomial, degree of derivative is 1 less than degree of original. How's that? Let's say so long as original is polynomial, so we have to include that. Awesome, thank you. Raise your hand if you have the same. Anybody else have the same connection there? Okay, what's a different connection? What's a different connection graphically or geometrically? What's a different connection? James and Matthew?
When the derivative is at the x-axis, that means the original function has a max or a min.
So if the derivative y prime is at the x-axis, what would its value be?
0.
0. So if the derivative value is 0, then y, not necessarily a max min, in this case it certainly was, and in the first case, but for sure it has what slope value? So we could quantify that, or we could summarize that as a horizontal tangent. Excellent. So a horizontal tangent exists on my original y, and y prime is 0. Great. Another connection. Different connection. All right, different connection. Andy and Colin?
For a function, if the original function is ax squared plus bx plus c, the equation of the derivative would be 2ax plus b.
Got you. So if my original was polynomial, right, ax squared plus bx plus c, then the derivative came from 2ax. Again, step down in degree. Yep. I'm going to count that as the same one, polynomial. Okay, so we've got 0 value for derivative. We've got horizontal tangent on original. What I want to do is look at positive versus negative derivative values and how that coincides with the behavior of the original. Right. So how does that coincide with the behavior of the original? Well, when my derivative values are positive, that is above the x-axis, what's true about my original function? Andy and Colin?
The original function is the slope is constant.
Absolutely. And so I would quantify that as increasing behavior on my original y corresponds to positive values in my first derivative. So then lastly, what can we say, Scott and Katie?
If it's decreasing
If what's decreasing?
the original,
Okay,
then the derivative.
I'm down. So, negative values, for us graphically, that means below the x-axis, right? Below the x-axis. For positive values, that means above the x-axis when we go to graph or plot. Awesome. Let's go ahead and apply our relationships and connections that we developed now to make pictures. So we're going to sketch derivatives as functions now, and we can always think back to, right, our y prime is measuring, a number that measures the instantaneous rate of change of my original, the slope of the original. So let's go ahead and find our sketching graphs of derivatives. We saw in our first activity how the derivative of a function doesn't always exist. What are some problem areas? Some problem areas for differentiability, that is, for a function's derivative to exist? Well, we saw in the very first activity that a corner or a cusp, an abrupt change in direction, resulted in a non-differentiable function at that x value where the cusp occurs. So we know that we're going to have undefined derivative values, right, whenever we have an abrupt change in direction, a corner or a kink in the original, or what we call a cusp, an abrupt change in direction. So we know that it's okay to have open circles. I'm going to go ahead and do my derivative here in green. And whenever I have this constant rate of change, a constant rate of change in my original function, where the slope is constant, I'll have a constant value for my derivative. That will translate into a horizontal line. So let's go ahead and take a look at this first one. When y, right, is a constant rate of increase, y prime will be a constant positive value. So I'll arbitrarily choose a positive value since we're not scaled here, we're just doing this qualitatively, so my y-axis isn't scaled for my derivative, but I'm going to choose some positive, not too high value because that's not too steep, but it'll be a constant line segment up until that corner kink or cusp. Recall that y prime is a number that measures, right, the steepness of my original function. After this corner, right, just past this x value where the cusp occurs, what's the slope of the original function? Positive or negative? Negative and steep or gradual? Well, I'd say steeper, so I'm going to go a little lower, more negative values away from the x-axis. So maybe I'll go down here. I know it's an open circle because the derivative does not exist at x equals c where that cusp occurred. I know that I have a horizontal tangent, right? A horizontal tangent on my original corresponds to what value on y prime? A 0 value. So right here, we'll have an x-intercept on my first derivative. And when y is increasing, y prime in green will be positive. It looks like the steepness is increasing, therefore my y prime values are increasing. So I'll have a linear segment here. And we've got a nice green y prime now. Key things. We got a horizontal tangent on my original. I'll fill that in as a 0, an x-intercept on my y prime. When y exhibited increasing behavior, I'll have positive values above the x-axis on my y prime. When y is decreasing, we'll have negative values, or we'll have below the x-axis picture. When my original was quadratic, right, if we assume that this is quadratic, then we'll say my derivative is linear. And that's okay for assuming right now, so long as we're dealing with polynomials. All right, guys, let's do another. This looks like part of a absolute value v. Yes? Absolute value v. I know I'll have undefined values of the derivative whenever my original f has corners or kinks, abrupt change of directions, or discontinuities. Right? There's no way for my left hand, for my function to be able to place a tangent line on my function if it's discontinuous. We don't know if we're supposed to put it on this side or in the middle, and so whenever the function's discontinuous, then no derivative value exists automatically. The value of the first derivative is undefined. So let's go ahead and see if we can't piece this together. When my original function is decreasing, I have negative y prime values. So if I did y prime in green again, arbitrary axis, no scale labeled on the y-axis. if I have constant decrease, I'm going to have a constant negative value. So that corresponds to a horizontal line segment. Is this steep or gradual? Fairly gradual, so I'm not going to go too low. Right? I'm not going to go too low, but I'm going to keep it constant until that cusp, at which point I'm going to jump up now to an equal and opposite positive value for the constant rate of change exhibited by the function on the next subinterval. So I'll go the equidistant away and continue on until discontinuity is automatically undefined derivative value, so I must have open circles at x equals b here. And now, what's the slope of the original y, right, in black for the rest of the interval? 0. So what values will y prime take on? 0. So I'm going to show that how. I'll be down here, open circle, but then along the x-axis. So when the original y has line segments, right, guess what? Y prime has line segments as well. It's just that if it was a slant line, then y prime will be horizontal line with the magnitude of the slope as its y coordinate. Easy cheesy? Good stuff. Let's take a look at another one. Yikes. That's not a parabola. That's not a line segment. So we're bumping it right up. What kind of function does this original y appear to be? What kind of function does this original y appear to be? Andrew?
Inverse sine?
Inverse sine?
And negative sine?
Oh, like a trigonometric.
Yeah.
For sure, right? For sure. Remember, inverse sine is restricted, right? So there's always a function. Inverse sine is restricted over just a short domain, so we don't get to do the increasing and decreasing and increasing again loop. But certainly part of this could be restricted, right? And then look at an inverse sine graph. This appears to be trigonometric. It might be inverse sine. I'm sorry, it might be sine, it might be cosine, because they're just transformations of each other. I definitely see this oscillating behavior, right? Forever back and forth between a max value and a min value brings to mind a sinusoid. So that could be sine or cosine. Good. So let's go ahead and start with horizontal tangents on my original correspond to zeros or x-intercepts on my derivative. So let's go ahead and fill those in first. That'll help us. Let's go ahead and do an arbitrary y prime. I know y prime will have zeros whenever y has horizontal tangents. So let's fill those in right now. So here we go. Looks like a 0 there. Looks like a 0 here. Looks like a 0 on y prime whenever y has horizontal tangents. Yes? Excellent. When y is increasing, then what kind of values does y prime take on? When y is increasing, what kind of values does y prime take on? Peter?
Positive.
Positive values. So graphically, will that be above or below the x-axis? Amanda? Above. And so we need to be above on any interval when y is increasing, y prime better be above. And yet we have to be back to 0 here. And so as my slope values increase, so does y prime. And then my slope values gradual, right? As they level off, they're getting lesser slopes. I need to get back down there. So it appears to me that I could do something like that. When y is decreasing, y must be negative, and leveling off again, I must be closer to the y-axis. When y is increasing, y prime is positive, and so on. If I continue with this behavior, it appears as though my y prime is very similar, right? It's very similar in nature to my original, but it's a measure of the original slope, not a measure of the original's y coordinates. Huh? Let's go ahead and try another. So what we'll do is we'll get started on our y to y prime graphs, and you're going to have a chance to practice. If we're assuming polynomials, then it's okay to do our step down, right? However, it's not okay to assume polynomials for all of our derivatives. In general, we can only apply the connections that we've summarized in our chart thus far. Okay? So here we go. If we're to look at it originally, we can go ahead and pick out those key points, what I referred to as key points. If we can find any zeros on our y prime, that's going to help us. So let's go ahead and find any zeros on y prime. I know that when y has a horizontal tangent, right, that corresponds exactly to a 0 on my y prime graph. And so at x equals -2, the value of y prime must be 0. What other x value is going to produce a 0 on y prime? Go ahead and tell the class when I call you. So what other x value is going to produce a 0 on y prime? Megan?
X equals +2.
X equals +2 because there's a horizontal tangent on y. So there must be a 0. Excellent. When y is increasing, I need positive y prime values. When y is decreasing, I need negative y prime values. When y is increasing, I need positive. And if we go so far as to assume polynomials, that looks like what degree polynomial, at least for this window. Right? What degree polynomial does that appear to be? Riley?
Third.
Third degree? So what could we infer the degree of our first derivative be? What do we think that's going to be? Second degree? So can we do it? Can we complete our sketch? Can we complete a second degree that satisfies our connections or relationships? So raise your hand if you have right side up parabola with those zeros. We're good to go. Okay. No problem. We can go ahead and continue on. All right. And we're going to go ahead and do these and check with our partner and see if we can generate each of these. And we should have a number 5. Awesome. We should have a number 5. We're also going to utilize our cell phones, right, and electronic devices appropriately. So we can go ahead and check with the y to y prime graphs key that's on our AP Calculus Moodle. So I want you to be checking these then with your cell phones or electronic devices. We'll go to the AP Calc Moodle webpage to check these. If you complete all and have checked them, then you can begin working on OTL, and we're going to come back for closure together at about 40. So we'll come back for closure together at about 40, but I want you to now practice the graphing. I'm going to circulate around the room. All right, if you have questions, catch my eye, and I'll pause the recording. We'll come back together for closure. Okay, ladies and gentlemen, so we'll answer these questions on the back. If you'd like to write down the answer, write down the original question as a point of reference, that would be great too. We just have 2 closure questions today. Firstly, what aspect of a function does its derivative measure? So what quality or aspect of an original function does the function's derivative measure? 2, please complete the chart for the appropriate intervals behavior, and then I'm going to go ahead and have you share your results. go ahead and share with the class your response number one. What aspect of a function does its derivative measure when I call on you? So what aspect of a function does the function's derivative measure? Gabby?
Instantaneous rate of change, x equals c.
Good. So our derivative measures the instantaneous rate of change of f at any point x equals c. What is that at any point? I think it's better view. We can quantify that as the slope, right? The slope of the graph at any point x equals c. Please complete the chart for the appropriate intervals of behavior. If y is increasing, then on the corresponding interval, what's true about y prime? Danny? Positive values, good. If y prime is negative, what does that indicate about y's behavior, Ben?
It's decreasing.
Decreasing, thank you. And what feature must occur on y if y prime equals 0? Right? What feature must occur on y if y prime equals 0? Tyler?
Horizontal line.
Good. A horizontal tangent must occur. It doesn't have to necessarily be a max or a min, right? It could just be a plateau point where we level off, but then continue increasing or decreasing afterwards. So it could be a plateau point, right? Like the cubing function. The cubing function has a horizontal tangent at x equals 0, right? But then it continues increasing afterwards. However, y prime is still 0 there. So we get around that. We can be safe to say that there's a horizontal tangent for sure. Excellent work, you guys. All right, you can use the rest of the time to begin working on your OTL. Catch up your fast if you haven't already. But don't back up and visit yet. We've still got a good 11 plus minutes. And so let's get a jump on our OTL so you have less work. Again, if you'd like to utilize your electronic devices to be checking with your key, that's fine. It's just not a time for texting or Snapchatting or video Snapchatting. So thanks for your cooperation with that. Nice work, you guys. And let me know if you have questions.